Hello my friends and welcome back to the You Can Do TV channel. Imagine the Viking ship museum standing strong, shielded by no-floods inflatable barriers against raging floods and fierce storm surges. These clever, water-filled barriers are stored away until needed, then quickly deployed, hugging the terrain, bending around corners and resisting even the strongest winds. One central pump fills multiple sections in no time, turning a potential disaster into a non-event. Already battle-tested during storm surges, these barriers prove that protecting history can be both smart and surprisingly agile. A flood protection exercise was successfully completed in Rubiera, Reggio Emilia, demonstrating the effectiveness of no-floods barriers under realistic emergency conditions. Organized by the Provincial Civil Protection of Reggio Emilia, the drill involved multiple municipalities and technical teams from the Emilia-Romagna region. The simulated flooding of the Trezenaro stream required rapid response. Within just 4 hours, technicians and volunteers deployed 2 barrier sections, totaling 800 meters, each with a double tube height of 125 centimeters. The exercise highlighted the barrier's fast deployment, adaptive design, and suitability for protecting residential areas, industrial sites, and critical infrastructure during extreme flood events. Formerly known as Boxwall, this upgraded solution has been integrated into Gentoft Municipality's flood protection strategy to safeguard Skovshoved Harbor and surrounding neighborhoods from extreme water levels and storm surges. Following extensive real-world testing of multiple barrier systems, EasyWall distinguished itself through patented hydroseal and hydrofoam technology, delivering exceptional sealing performance with minimal seepage. During live deployment, crews installed 1 kilometer of barriers in just 3 hours and dismantled them just as quickly. Lightweight construction, intuitive assembly, and rapid response capability make EasyWall a critical interim solution within long-term climate adaptation framework. The installation of the first 80 meters of the SCFB system, part of a total 300-meter flood defense in Spakenburg's historic harbor, Netherlands, was completed in record time. The modular design allowed rapid assembly, with each section efficiently positioned and secured. This initial deployment demonstrates the system's speed, reliability, and suitability for protecting critical waterfront infrastructure, ensuring immediate flood resilience while maintaining operational efficiency in a busy harbor environment. The no-floods reusable flood barrier revolutionized repair works at a wetland dam, allowing major restoration without disturbing the ecosystem. Smaller streams were secured with FlexWall units, while a 200-meter twin-tube Pro dammed the lake's water flow. Quick to deploy and water-powered, the barrier creates strong, temporary protection with minimal personnel and equipment. Its versatility safeguards construction sites, critical infrastructure, and the environment, providing a sustainable, turnkey solution for water management and flood control. QuickDam outdoor products provide a fast, reliable solution for temporary flood protection in residential, commercial, and infrastructure environments. Designed for rapid deployment, these water-activated barriers expand automatically when exposed to water, forming an effective seal against advancing floods. Unlike traditional sandbags, QuickDam products require no filling, no heavy equipment, and minimal manpower, allowing users to respond immediately to rising water levels. The lightweight, compact barriers are easy to transport and store, yet highly effective once activated, absorbing and retaining water to create a stable protective wall. Suitable for doorways, garages, construction sites, and outdoor facilities, QuickDam outdoor products help reduce property damage, protect critical assets, and improve emergency response efficiency. Their reusable, eco-conscious design makes them a practical and dependable choice for modern flood mitigation. The heavy-duty flood barrier C48C122 system demonstrates a fast, efficient, and labor-optimized installation process designed for emergency flood defense. The process begins with placing the C122 metal supports at 122 centimeter intervals. Each support is unfolded and secured in an upright position using an integrated snap-lock mechanism, ensuring immediate stability. Next, the supports are structurally connected with link bars, forming a continuous load-bearing frame. C122 metal sheets are then mounted by sliding their keyhole cutouts over the protruding sections of the link bars, creating a rigid retaining wall. Garland chains are fixed to the square holes on the front beam using carabiners, after which the chain lengths are laid along the ground behind the barrier. A waterproof membrane is rolled out and secured with one sealing clip per section. Finally, the garland chain is lifted, wrapped inside the membrane, and fastened with cable ties, completing a robust, pressure-resistant flood protection system ready for deployment. 2 workers installed 40 meters of barrier with a height of 1.22 meters in just 50 minutes, without rushing. The installation comprised 33 barrier sections, highlighting the system's modular and scalable design. At Beals Corner in Bewdley, flood protection is managed with a tiered barrier system along the River Severn. Rainfall from the Welsh Mountains reaches the area after about 3 days, allowing advanced deployment. 3 barrier sets are available, activated at defined water level thresholds. With river levels nearing 3.8 meters, the lowest and second thresholds were deployed, protecting homes and businesses and allowing the town to remain operational despite flooding. Fast, reliable flood protection begins with No Flood's EasyWall. This advanced, tool-free barrier deploys in minutes, combining lightweight modular design with exceptional stability. Engineered for near-zero seepage, it outperforms traditional ABS barriers, delivering dependable protection across diverse flood conditions with unmatched ease and confidence. Coastal protection in Lubmin, Germany, relies on Secutech soft rock sand containers to defend against storm surges and erosion. In this high-risk seaside area, the solution forms a geotextile wall built directly inside the dune as a last protective barrier. Around 33,000 sand containers are filled with local sand, quickly sewn closed and installed layer by layer. This precise construction method ensures optimal alignment, structural stability, and long-term resistance against coastal erosion and extreme wave action. Wave testing was carried out on the Agger self-closing flood barrier to demonstrate its ability to perform under extreme conditions. A 5-meter wide test section with a retaining height of 1.5 meters was exposed to powerful waves exceeding 1 meter, simulating a rare 1 in 4,000 year storm event. Throughout the test, the barrier activated automatically, holding back the water without the need for power or human intervention. The results confirmed a robust and reliable solution that can be extended to unlimited lengths, supporting long-term flood resilience for modern, climate-ready cities. The gate has been repositioned for the first time from Basin B where it was cast. The structure measures 50 meters in width and 21 meters in height and is constructed entirely of reinforced concrete. Its function is to hydraulically isolate the construction basins during controlled flooding for tunnel element transport. The gate incorporates 8 internal buoyancy chambers that allow precise regulation of displacement by adjusting water levels, enabling controlled lifting, lowering, and horizontal movement with high operational stability. Tetropods are specially designed concrete blocks used to dissipate wave energy and protect coastlines and riverbanks from erosion. Among various types of breakwater units, tetropods are the most widely recognized and commonly used in Japan. Their unique, four-legged shape allows them to interlock effectively, reducing the force of incoming waves. The manufacturing process starts with assembling steel formwork, followed by pouring fresh concrete into the molds. After the concrete is properly cured and gains sufficient strength, the formwork is removed. The completed units are then repositioned, inspected for quality, and prepared for transportation and installation at coastal protection sites. A crane-equipped barge is installing reinforced concrete units, commonly known as tetropods, to construct a breakwater or coastal revetment. The barge's large crane lifts and positions these specially shaped cross-like blocks, designed to interlock and resist displacement by waves. This operation is critical for protecting the shoreline from erosion and the impact of strong waves, ensuring long-term coastal stability and safeguarding nearby infrastructure. Each tetropod is carefully placed to form a robust barrier, demonstrating the combination of precision engineering and marine construction techniques required for effective coastal defense. The construction of the western flood protection at the Bogawanto River estuary is a comprehensive coastal and river defense project designed to secure the estuary and surrounding infrastructure. The project begins with rigorous safety briefings for all personnel on site, followed by the preparation of reinforcement steel and concrete batching. At the batching plant, concrete is produced for various elements, including standard blocks 1x1x1 meter, precast units, and tetropods weighing 4 ton and 7 ton. Quality control plays a critical role, with slump tests and compressive strength tests conducted regularly to ensure compliance with design specifications. Precast units are carefully documented and stored in the stockyard before being transported to the jetty installation site. Installation activities include placing the 1x1x1 meter concrete blocks, as well as the larger 4 ton and 7 ton tetropods, which are strategically positioned to dissipate wave energy and protect the jetty. Simultaneously, embankment works reinforce the riverbanks, reducing erosion risks and enhancing overall structural stability. The coordination between batching, quality control, and on-site installation ensures a streamlined workflow. By December, significant progress is made in assembling the precast elements, placing blocks and tetropods, and constructing the river embankments. The project highlights a combination of precise engineering, heavy-duty material handling, and strict adherence to safety and quality standards, contributing to the long-term resilience of the Bogawanto River estuary. Coastal zones are increasingly at risk from erosion, storm surges, and rising sea levels. Rising demand for sustainable, cost-effective alternatives has driven the adoption of engineered solutions that combine resilience, efficiency, and ecological compatibility. TechFab geotextile tubes offer such a solution, providing technically advanced coastal protection and land reclamation. These geotextile tubes function as engineered coastal structures, including breakwaters, groins, revetments, and seawalls. Constructed from high-strength woven or composite geotextiles, they provide structural stability while allowing water to pass through pores, retaining the sand infill. Tube dimensions and arrangement can be precisely designed according to site-specific hydrodynamic and reclamation requirements. Compared to conventional rock or concrete solutions, TechFab tubes reduce construction time, cost, and labor, using locally available infill materials. The installation requires minimal equipment, integrates seamlessly into the environment, and supports ecological processes such as silting and algae formation. Construction on the National Canal and the Quistepa Grand Canal is progressing steadily, combining large-scale earthworks, reinforced concrete structures, and hydraulic engineering systems. Excavation and dredging operations continue along key sections to ensure the required channel depth and flow capacity. Concrete lining and embankment reinforcement are being installed to prevent erosion and maintain structural stability. Mechanical and electrical installations for water control, gates, pumps, and sluices are underway at major junctions. Quality control procedures, including soil compaction tests, concrete strength verification, and flow simulations, are conducted throughout. The project aims to improve irrigation, flood control, and regional water management efficiency while adhering to stringent environmental and safety standards. The Al Shark Gate Infrastructure Project, managed by Al Rusun Contracting Company, involves the comprehensive development of essential urban infrastructure. Roadworks include excavation, subgrade preparation, asphalt paving, and the construction of sidewalks and curbs to provide durable and safe access throughout the area. A modern water supply network is being installed, featuring pipelines, valves, and connections to ensure reliable distribution. Stormwater drainage systems are integrated to control runoff and prevent flooding. The electrical network covers both high and low voltage lines, along with transformers and junction boxes for stable power supply. Street lighting is installed according to technical specifications, ensuring visibility and safety. The project follows strict quality control procedures, sustainable practices, and design compliance to deliver resilient and long-lasting infrastructure. The Border Crossing Road project to the Sultanate of Oman utilizes crawler bulldozers for precise and efficient earth-filling operations. These machines handle large volumes of soil, spreading and compacting fill material to achieve the required road subgrade elevation. The bulldozers. Tracks provide excellent traction and stability on uneven terrain, ensuring uniform layering and minimizing settlement. Operators follow design profiles, adjusting blade angles and push sequences to maintain slope and grade accuracy. Compaction is monitored throughout to guarantee stability and load-bearing capacity. This mechanized approach significantly accelerates construction, reduces manual labor, and ensures a durable foundation for subsequent asphalt paving and road infrastructure. In the constantly moving ocean, where every wave carries immense yet untapped energy, swell waveline energy magnet dot. The waveline magnet developed by Seawave Energy is an innovative wave energy converter designed to harness ocean surface motion and convert it into mechanical power. Comprising a series of flexible, interconnected floating assemblies linked by a central spine power system, the device embraces the water's surface, allowing it to move in tandem with passing waves rather than resisting them. This controlled, frictionless interaction enables regulation of how much energy is extracted from rising and falling waves. The modular, low-mass design supports rapid deployment and low maintenance, with materials that can be recycled and sourced without specialized manufacturing infrastructure. Swell's R&D indicates the technology has potential for high energy output, scalable deployment in diverse wave climates, and applications including electricity generation. The departure of the first 4 floodgates marks a critical logistical phase in the overall project execution. The operation begins at the San Giorgio production plant, where the completed gates are prepared for transport following final inspections and load securing procedures. Specialized heavy haul vehicles are deployed to manage the oversized dimensions and weight, ensuring controlled travel along a predefined route. Upon arrival at the port of Trieste, the gates undergo a carefully coordinated transshipment process. Port cranes and lifting frames are used to transfer each structure from land transport to the marine vessel with precise load balancing and continuous monitoring. Temporary positioning, alignment, and securing operations are carried out to meet maritime transport standards. After completion of boarding activities, the convoy departs Trieste, initiating the sea transport phase. This milestone demonstrates the integration of industrial manufacturing, heavy logistics, and port operations, ensuring the safe and efficient delivery of critical infrastructure components. Intercontinental Shanghai Wonderland represents a radical departure from conventional hotel construction, gaining global attention for its underground design. Built inside an abandoned quarry, the eco-friendly hotel extends downward rather than rising upward, suspended along the steep wall of an 88-meter deep pit. Covering approximately 100,000 square meters, the project transformed an industrial scar into a functional landmark. Construction posed exceptional challenges, from piling and material transport to crane installation on near-vertical slopes. The final design followed the quarry's natural geometry, anchoring the structure to the pit edge and curved rock face. Cliff stability was ensured using pre-stressed anchor cables and thousands of rock bolts, reinforcing the quarry wall like structural stitches. After 12 years of construction and more than 40 patents, the project stands as a benchmark in engineering innovation and sustainable adaptive reuse. The Intercontinental Shanghai Wonderland Hotel stands as one of the most technically ambitious hospitality projects ever completed. Constructed within an abandoned quarry approximately 88 meters deep in Shanghai's Songjiang district, The project is recognized as the world's first luxury hotel built almost entirely below ground level. More than 70% of the structure lies beneath the natural terrain, including 2 fully submerged floors beneath an artificial lake. The hotel covers a total floor area of approximately 100,000 square meters and consists of 18 levels, with only 2 floors visible above ground. The primary structural system is directly anchored into the quarry's near-vertical rock face, transforming the geological formation into a load-bearing component. Over 500 rock anchors and nearly 100 pre-stressed anchor cables, some extending up to 35 meters, were installed to stabilize the cliff. The reinforced rock surface exceeds 700 square meters, ensuring long-term structural and geological safety. One of the hotel's defining engineering achievements is its underwater restaurant and guest rooms, which employ high-strength, pressure-resistant glass and advanced waterproofing systems. The subterranean design significantly improves thermal insulation, reducing energy demand for heating and cooling while enhancing environmental performance. Construction spanned more than 12 years, overcoming unprecedented challenges related to vertical excavation, material transportation below grade, and precision installation on steep rock walls. Throughout development, the project generated over 40 patented technologies, covering cliff stabilization, underground structural systems, and sustainable construction methods. Since completion, the intercontinental Shanghai Wonderland has become a global architectural landmark and a benchmark case study for adaptive reuse of industrial sites. The project demonstrates how extreme terrain and abandoned infrastructure can be transformed into high-value, technically advanced, and environmentally responsible developments, redefining the boundaries of modern engineering and architectural design. The EcoSmart Breakwater is a sustainable concrete solution developed for smart applications in marine environments. Each individual boulder, made with 2.5 quintals of posidonia and 60 quintals of recycled aggregates from construction and demolition waste, is structurally designed to dissipate wave energy, stabilize rubble mound breakwaters, and protect harbor infrastructure from erosion. Before transportation and installation, every boulder is tested in a laboratory environment using embedded sensors. These sensors monitor mechanical behavior and hydraulic response under simulated wave action, ensuring performance, stability, and durability meet design requirements. Only after successful validation is the boulder transported for placement, as demonstrated in the rubble mound breakwater at Otranto Harbor, Italy. At the German portal in Puttgarden, the Fehmarnbelt tunnel is advancing using the cut-and-cover method. More than 100 meters of tunnel structure have been cast in the excavation, with segments backfilled and sealed by watertight bulkheads. Progressive stone placement forms a new coastal dam, enabling controlled flooding and removal of the temporary cofferdam. Hot tapping is a specialized pipeline operation that allows for the connection of a new branch or the installation of a valve without interrupting the flow of the existing pipeline. This method is widely used in oil, gas, and water distribution networks, where continuous service is critical. The operation begins with the installation of a hot tap fitting onto the live pipeline. The fitting is typically welded or clamped to the pipe, forming a secure, pressure-tight connection. Once the fitting is in place, a specially designed hot tap machine is mounted. The machine includes a rotating cutter, which penetrates the pipe wall while maintaining system pressure. The cutout section of the pipe, known as the coupon, is retained within the machine to prevent it from entering the flow stream. During the cutting process, careful monitoring of pressure and flow conditions ensures safety and system integrity. After the tap is completed, the machine is removed, leaving the new branch or valve fully connected and ready for operation. This technique eliminates the need for shutdowns, reducing downtime and maintaining continuous service to end users. Hot tapping is particularly advantageous in congested urban networks or critical industrial facilities, where shutting down the main line could result in significant operational or economic impacts. Trained personnel must follow strict safety protocols, including pressure control, leak detection, and proper equipment handling to mitigate risks. In addition to connecting new lines, hot tapping allows for emergency interventions, pressure monitoring points, and sampling stations to be installed without service interruption. The reliability and flexibility of this method make it an essential technique in modern pipeline management, combining engineering precision with operational efficiency to ensure safe, continuous, and uninterrupted flow in pressurized pipelines. The Rekind offshore pipeline and mooring tower project marks a major milestone in offshore engineering in Indonesia and Southeast Asia. Awarded by ExxonMobil, the EPCI scope includes the installation of a 20-inch diameter offshore pipeline with a total length of 23 kilometers, along with a mooring tower system weighing approximately 5,000 tons. This project represents the first tower yoke mooring system implemented in the region, reinforcing Rekind's role as a pioneer in offshore EPC technology. Located offshore Tuban, East Java, the mooring tower plays a critical role in simultaneously mooring the FSO and transferring crude oil from the onshore processing facility through a subsea pipeline. The structure stands 84 meters high from the seabed and supports continuous production from the Banyu Urip Bojo Nagoro oil field. The mooring tower consists of 4 main modules: the jacket structure with skirt piles, the topside module, and the yoke that connects the tower to the FSO. Engineering began with multidisciplinary collaboration with the technology provider in Houston, followed by detailed design in Indonesia using advanced 3D modeling software such as PDMS. Fabrication was carried out locally by skilled domestic workers. Offshore transportation covered a distance of approximately 690 kilometers and required detailed marine engineering, stability analysis, and weather assessment. Installation utilized a 3,000-ton derrick barge, hydraulic piling hammers, and continuous leveling surveys. Subsequent phases included subsea spool installation, topside lifting, yoke installation, and final connection of jumper hoses, mooring lines, and control systems. The successful completion demonstrates Rekind's world-class offshore construction capability. Solitaire is one of the largest and most advanced pipelay vessels in the world, setting new benchmarks in offshore pipeline installation. Operational since 1998, the vessel has continually improved her efficiency and capabilities. Designed along the same principles as Lorelei, Her elongated, ship-shaped hull ensures excellent stability and workability in challenging offshore conditions. With a pipe carrying capacity of 22,000 tons, Solitaire can operate with reduced reliance on offshore pipe supply, even in hostile environments. Full dynamic positioning enables precise maneuvering in congested areas, enhancing operational safety. Solitaire holds records for ultra-deepwater pipeline installation. In 2005, her S-lay capacity was upgraded to a holding force of 1050 tons, supporting the heaviest pipelines. By 2007, she set a world record, laying pipe at 775 meters depth. High cruising and laying speeds, combined with substantial capacity, make Solitaire highly competitive for global pipelay projects. The Bekong wellhead platform was installed by McDermott for Sapura OMV in June and July 2019, using McDermott's derrick barge DB30. The platform consists of a four-legged jacket and a topside module, forming part of the Pan-Malaysia Transportation and Installation Contract. Located in the SK-408 field offshore Sarawak, East Malaysia, in 80 to 90 meters of water, the platform weighed approximately 200 metric tons. The jacket piles and conductors were loaded from a fabrication yard and transported over 8 days to the offshore site on the Windposh 3301, towed by tug Ina Pearl. The topside was transported separately on the barge EOS 281, towed by tug Swiver Challenger. Offshore installation of the jacket took 8 days, from June 24th to July 3rd. The jacket was side-lifted, up-ended, and set on the seabed using DB30's main crane. Each leg has 5 piles, 1.219 meters in diameter, and 178 to 181 meters long, driven with hydraulic hammers. Following boat landing and completion works, the topside was lifted and installed in 1.5 days. The platform was fully completed on July 4, 2019. At the NPCC fabrication yard, steel structures undergo a precise and systematic production process. The workflow begins with beam cutting, where structural beams are accurately measured and cut to specification. Parallelly, plate cutting is carried out to produce steel plates of exact dimensions required for assembly. The next stage is subassembly, where cut beams and plates are pre-assembled into modules, ensuring alignment and fit before full fabrication. Completed subassemblies are then moved for transportation to blasting and painting, where surfaces are treated and coated to provide corrosion protection. Finally, the stacking process organizes finished modules efficiently, readying them for shipping or further integration into offshore or onshore projects. This workflow ensures high-quality fabrication, precision, and safety throughout. In Vietnam, the loadout of a massive 12,733-ton jacket marked the initial phase of the offshore operation. Due to its extraordinary size, 131 meters long, 81.7 meters wide, and 56 meters high, Mammoot's strand jack system was employed. The jacket was pre-assembled on skid beams with a launch truss, using breakout jacks to initiate controlled movement. Once released, the strand jacks and winches executed the main pulling operation, carefully guiding the structure onto the loadout barge. The barge was equipped with external high-capacity submersible ballast pumps, fully synchronized with the internal ballast system, allowing precise deballasting. Operations were monitored and controlled from the barge bridge, ensuring safety and accuracy. This methodical process demonstrates a smarter, safer, and stronger approach to handling ultra-heavy offshore structures. The Safe Coast project demonstrates advanced coastal protection using Terrafix geotextiles in the construction of modern groins and revetments. Terrafix 773G43, a needle-punched woven/non-woven geotextile, serves as an effective separation and filter layer, providing protection and encapsulation in hydraulic engineering applications. With decades of proven performance, Terrafix offers exceptional robustness against harsh installation conditions, flexibility to adapt to soil irregularities, and a high interface friction angle, ensuring structural stability. Its long-term filter performance, greater non-woven thickness, precise opening size, and superior shear behavior make it ideal for revetment mattresses and other coastal structures. Available in rolls up to 5.90 meters wide, Terrafix complies with ISO 9001 standards and is approved by the German Federal Waterways Engineering and Research Institute. By integrating geosynthetics like Terrafix, the Safe Coast project enhances shoreline resilience, prevents erosion, and ensures sustainable protection against wave action and storm surges. The construction of the Aasta Hansteen offshore platform represents one of the most demanding offshore developments ever undertaken on the Norwegian continental shelf. Located in the Norwegian Sea at a water depth of approximately 300 meters, the field is characterized by harsh weather, strong currents, and complete isolation from existing offshore infrastructure. No prior installations existed in the area, requiring entirely new engineering solutions. Aasta Hansteen is the first spar platform installed on the Norwegian continental shelf and, at the time of construction, the largest spar platform in the world. The substructure weighs approximately 46,000 tons, measures 200 meters in length, and has a diameter of 50 meters. The topside, weighing around 24,000 tons, houses a conventional gas processing facility. The hull was uniquely constructed in a horizontal position in South Korea using Hyundai's megablock fabrication method, where large structural blocks are assembled onshore before final integration. After completion, the hull is transported to Norway, upended offshore, and mated with the topside. The project faced significant complexity, including delayed engineering progress and an intense construction phase involving up to 2,000 personnel. Piping work alone required around 800 specialists to complete systems prior to hydrotesting, pressure testing, and valve installation. Despite fabrication abroad, more than half of the equipment packages and nearly all subsea systems were supplied by Norwegian manufacturers, many based in northern Norway. Gas export is enabled by the 482-kilometer polar lead pipeline, the first subsea pipeline to cross the Arctic Circle. Designed for future tie-ins, both the platform and pipeline open new opportunities for long-term gas development in the region. Rising between Denmark and Germany, the Fehmarnbelt Tunnel stands as one of Europe's most ambitious construction projects. Stretching 18 kilometers beneath the Baltic Sea, it will become the world's longest immersed tunnel and the fastest fixed link between Scandinavia and Central Europe. At Rodbyhavn, Denmark, a vast production facility forms the heart of the operation. Here, enormous concrete tunnel elements are cast inside dedicated production halls. Each standard element is 217 meters long, weighs more than 73,000 tons, and contains 2 road tubes, 2 railway tubes, and a central service corridor. Once completed, the elements are sealed, floated from dry dock, and towed to their exact offshore positions. Precision ballast systems, seabed sensors, and hydraulic guidance allow each unit to be lowered into a dredged trench with accuracy measured in millimeters. Powerful sealing systems lock the elements together, creating a watertight structure beneath the sea. The trench is then backfilled with sand, gravel, and protective rock, allowing natural currents to gradually restore the seabed. When completed, the Fehmarnbelt tunnel will reduce travel times to minutes and form a vital link in a new, sustainable European transport corridor, connecting regions, economies, and people for generations to come. The Kisanuma Bay Crossing Bridge, also known as Kanai Ohashi, is a major coastal infrastructure project on the Sanriku Expressway in Miyagi Prefecture in northeastern Japan. With a total length of approximately 344 meters, including 680 meters spanning open water, the bridge represents one of the most significant marine bridge projects in the Tohoku region. It was developed as a key element of post-disaster reconstruction following the 2011 Great East Japan earthquake and tsunami, restoring critical transportation links along the Pacific coast. The bridge features a 3-span continuous steel cable-stayed structure, with a 360-meter main span, making it the longest cable-stayed bridge in the Tohoku area. 2 reinforced concrete pylons rise to a height of approximately 115 meters above sea level, supporting the steel box girder deck through a multi-cable stay system. This structural configuration minimizes the number of piers required within the bay, reducing environmental impact, maintaining navigational clearance, and improving structural efficiency over long spans. Design criteria place strong emphasis on seismic resistance, wind stability, and durability in a corrosive marine environment. Advanced seismic isolation and energy dissipation technologies were incorporated to ensure performance during major earthquakes. Aerodynamic deck profiling and detailed wind analysis were conducted to secure stability under strong coastal winds. Construction was carried out over more than 6 years and presented considerable engineering challenges. These included deep water foundations, complex seabed geology, and strong tidal currents within Kisanuma Bay. Offshore foundation works were followed by the erection of the pylons and the incremental installation of large steel girder segments using heavy-lift marine cranes. Each segment was precisely positioned and aligned to meet strict tolerances required for cable-stayed construction. Since opening to traffic in 2021, the Kisanuma Bay Crossing Bridge has significantly improved regional mobility, shortened travel times, and enhanced disaster resilience along the Sanriku coastline. Beyond its functional role, the bridge stands as a symbol of advanced Japanese bridge engineering and the region's long-term recovery and renewal following one of the most severe natural disasters in modern history. With a cumulative installed capacity exceeding 200 million kilowatts, the completed energy project portfolio demonstrates an exceptional level of technical capability and engineering expertise on a global scale. The Three Gorges Dam, with an installed capacity of 22,500 megawatts, remains the largest hydropower project ever constructed, integrating large-scale flood control, navigation systems, and high-capacity power generation within a single hydraulic structure. The Jingping Hydropower Dam, rated at 3,600 megawatts, stands as the highest double-curvature arch dam in the world, engineered to withstand extreme geological and seismic conditions. The Wudong hydropower complex, with a capacity of 200 megawatts, houses the world's highest underground powerhouse, reflecting advanced mastery in deep excavation, cavern stability, and underground structural design. Internationally, the Tekeze Dam in Ethiopia, 300 megawatts, represents Africa's highest concrete arch dam, optimized for local hydrological and topographical conditions. In the thermal power sector, the Rabi power plant in Saudi Arabia, 320 megawatts, features the largest single-unit capacity in the Middle East, incorporating high-efficiency and highly reliable power generation technologies. Precision engineering defines the construction of Dubai Creek Tower from the very first stage. High-capacity concrete batching begins with the controlled mixing of desert sand and cement. Engineered to meet demanding structural requirements, 6 concrete pumping trucks work in perfect synchronization, ensuring a continuous and stable pour. More than 200 tons of reinforced steel are positioned to form a dense and resilient foundation framework. The operation continues through the night, supported by 840 truck deliveries that maintain an uninterrupted supply chain. Laid end-to-end, the installed reinforcement extends an extraordinary 325 kilometers. Over a continuous 30-hour concrete pouring operation, coordination, timing, and quality control remain critical at every step. When the final pour is completed, the mission is accomplished, establishing a solid foundation for one of the world's most ambitious architectural landmarks. During the rainy season, the Panama Canal maintains continuous monitoring of Gatun and Alajuela lakes as water levels approach maximum operating limits. If the trend continues, preventative discharges may be carried out to protect nearby communities, ensure hydraulic stability, and maintain safe, reliable canal operations. Via desertification, with an annual average of 14,000 square kilometers of land degraded by the end of the last century. Today, that figure has been reduced by about 200 square kilometers per year, thanks to decades of sustained effort. Since 1949, and especially after the launch of the 3 North Shelter Belt program in 1979, generations of foresters and thousands of companies have transformed vast desert regions into continuous green belts, marking one of the world's largest ecological achievements. Rising from the Nevada desert, this project marks the construction of the world's first utility-scale molten-salt power tower. Located near Tonopah, it redefines how solar energy is produced and stored. Using concentrated solar power with molten-salt thermal storage, the 110-megawatt facility captures the sun's heat by day and releases it on demand, delivering up to 10 hours of full-load energy even after sunset. More than a technological milestone, the project is a success story for U.S. innovation, creating over 300 jobs and supporting more than 1,000 workers at peak construction. Each year, it generates over 500,000 megawatt-hours of clean electricity, powering 75,000 homes during peak demand. With no fossil fuel backup and reduced water use, the facility delivers reliable, emission-free energy day and night.